Imagine a place in the universe where the rules we live by simply stop working. In our daily lives, we are used to things having a top, a bottom, and a predictable path through time. But deep in space, there exist objects so massive and compact that they warp the very fabric of reality around them. These are black holes. They are not literal holes in the sense of an empty void, but regions of space where gravity has become so intense that nothing, not even light, can escape its pull. They represent the ultimate limit of our current understanding. To understand a black hole, we first need to understand how gravity works on a fundamental level. Albert Einstein taught us that space and time are not empty, static voids, but part of a single, flexible fabric called spacetime. Think of this fabric like a large, stretched-out rubber sheet. If you place a heavy ball on it, the sheet curves downward. Massive objects like stars and planets do the same to spacetime. This curvature is what we feel as gravity. A black hole is what happens when mass is concentrated into a point so small that the curve becomes a bottomless pit. The boundary of this gravitational pit is known as the event horizon. This is the point of no return. Beyond this invisible shell, the speed needed to escape the black hole's pull becomes greater than the speed of light. Since nothing in the known universe can travel faster than light, anything that crosses this line is trapped forever. From the outside, the event horizon looks like a sphere of perfect darkness, often surrounded by a swirling disk of superheated gas and dust, glowing brightly as it is accelerated toward the center by immense forces. A helpful way to visualize the motion of space near a black hole is the cosmic waterfall analogy. Imagine a wide river flowing toward a massive waterfall. If you are swimming upstream, you can move away from the edge as long as you swim faster than the current. But as you get closer to the drop-off, the water speeds up. The event horizon is the exact point where the river flows at the speed of light. Once you pass it, space itself is moving inward so fast that no matter how hard you swim, you are pulled deeper. Near a black hole, time itself begins to behave strangely. This is due to gravitational time dilation. If you were to watch a clock falling toward a black hole from a safe distance, you would see its hands move slower and slower as it approached the event horizon. To your eyes, the clock would appear to freeze in time, its light fading into a faint red glow before disappearing entirely. To the clock itself, however, time would seem to pass normally. This disconnect between perspectives is one of the most counterintuitive aspects of the laws of relativity. If you were to cross the event horizon, you would experience a process colloquially known as spaghettification. Because the gravity increases so sharply over short distances, the pull on your feet would be significantly stronger than the pull on your head. This tidal force would stretch any object into a long, thin strand of atoms. While this sounds violent, for a truly massive black hole, the event horizon is so large that you might not feel anything at all as you pass through it. The real trouble begins only as you approach the very center of the void. At the very heart of a black hole lies the singularity. According to our current mathematical models, this is a point of infinite density and zero volume. Here, the curvature of space-time becomes infinite, and the laws of physics as we know them break down completely. General relativity, which describes the big things in the universe, and quantum mechanics, which describes the very small, refuse to work together at this scale. The singularity is a math error in our understanding of the universe, a place where our current theories simply stop making any sense. For decades, scientists believed that black holes were eternal, but Stephen Hawking changed that. He proposed that due to quantum effects at the event horizon, black holes actually emit a tiny amount of radiation over immense periods of time. This Hawking radiation causes the black hole to lose mass and eventually evaporate. This discovery led to a major problem called the information paradox. If a black hole disappears, what happens to the information about everything that fell into it? In physics, information is supposed to be permanent and is never meant to be truly destroyed. One potential solution to this paradox is the holographic principle. This theory suggests that the information about an object falling into a black hole isn't lost, but is instead encoded on the surface of the event horizon. Much like a 2D hologram, it can create the illusion of a 3D image of the 3D reality of the others inside a black hole might be a projection of 2D data so it is outer boundary. If this is true, it might apply to the entire universe, suggesting our reality is a projection from an edge. Exploring black holes is more than just an exercise in theoretical physics. is a quest to find a unified theory of everything. By studying these extreme environments, we are pushed to reconcile the largest and smallest scales of reality. We may never be able to see inside a black hole or visit a singularity, but by looking at the edges of what we know, we gain a clearer picture of the universe's fundamental nature. The darkness of a black hole is not an end, but a gateway to a deeper understanding of existence.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.